Hello everyone. So today we'll start with week 10's content, which is mostly cost curves and cost minimization, profit maximization. So if you have any questions, please share it in the chat box, or if you want, you can also just unmute yourself and speak. So just give me a moment. I will connect the screens, etc. In the meantime, if you have any questions from the content or from the previous weeks, anything, please let me know.
Madam, am I audible?
Yes. Could you speak up a little?
Yes, madam. There was a question of assignment 8 last.
Yes. I remember. I haven't forgotten. So I asked the TAs to look at the question, and they have posted an answer, and I'm still not convinced about the answer. Actually, what they have posted. That's why I don't want to discuss it, because I don't actually agree with the solution. So I couldn't get any time to discuss it with them. I mean, they are busy. So I will try to follow it up with them again. But in the meantime, if you want, you can read the solution they have posted. If you are okay with it, it's fine. But I mean, I don't feel convinced about the solution they posted. I know how they got the answer, but I'm still not convinced about the solution they posted. So I will come back to you. If I get any clarity in the middle of the week, I'll post it in the shared slides and notes. Okay. If that doesn't happen, then we can discuss it next week. So they have shared a detailed solution because I asked them to, but I'm just not convinced about that solution. That's the problem. You have a valid question. So, I mean, I understand why you are stuck with that question, but I don't want to give you a wrong answer. That's why I'm not discussing it. Okay, so we'll start with this week's content. Before that, other than those questions in week 8, also, yeah, one more thing. In week 8, there are 2 other questions also. One, let me just see which questions these were. This was question number. Just give me a moment. Yeah, question 6 and 7. So the answer for question 6 and 7 in assignment for week 8, in the quiz, it's wrong. Okay, that we also did that, we derived that MPK, MPL, we derived in the class also in week 8. And the answer in the quiz, like what you see in the quiz, the options they have given, minus root k by L, minus root 7k by L, minus root L by k, blah, 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 they're all wrong. Okay, and the correct answer which they have given in the answer, that is also wrong. Okay, in the solutions, they have uploaded some detailed solutions. So if you see, week 8, they have uploaded a new set of solutions. Week 8 assignment solution, if you go and see, they have uploaded a solution in which they have done that correctly for week question 6 and 7, or 7 or 8, whichever that is. The question is basically a firm produces output using 2 inputs, labor and capital. Production function is Q is equal to 10 L to the power half K to the power half, where Q is the output produced, L is the units of labor, and K is the units of capital employed. What will be the marginal rate of technical substitution of labor for capital? Okay, so now in this question, they have asked you 2 things. One is marginal rate of technical substitution of capital for labor, and one is of labor for capital. Okay, so what we derive in class is MPK by MPL. But if you're doing it the other way around, it will be MPL by MPK. Okay, that is the only trick in this question. But the differentiation, if you see the solutions they have uploaded, in that it is correct. In the answer given in the quiz, the answer is wrong because they've done the differentiation wrong. If you differentiate that function to derive MPL and MPK, that is not what you get. You will get K by L and L by K as the answer, not root K by L and root L by K. There will be no under root. Okay, so that answer in the quiz is wrong also. I just wanted to point it out. And it is corrected in the solutions they have uploaded, but the quiz is still wrong. And I have mentioned it to them also. It may be some technical issue with the platform also. That is very much possible. But just so you know that the answer in the solutions is right, in the quiz it's wrong. Okay. So apart from this, is there any other question?
There is one more question on my part.
Which question?
Assignment 6. Just give me a moment. I'll look into the question and tell you. In assignment 6. Question number 6.
Okay. Suppose the utility function of an individual is given by u is equal to 3 log x plus 2y, and the budget set is given by x plus py is less than or equal to I. If p is equal to 2 and I is equal to 10, which of the following bundles maximizes individual's utility? Okay, so what is the issue with this question?
So when I check the answers by using calculator, 2 comma 4 gave higher utility than 3 comma 3.5.
2 comma 4 you're saying gives higher utility, like you
Yes,
computed it taking these values, but what did you get after doing the calculus thing? Did you do the utility maximization?
yes, madam. If I did that, I got 3 comma 3.5.
Sorry.
If I did that utility maximization du by d equal to 0, I got 3 comma 3.5. But
Okay.
according to the question, utility ought to be maximum for which bundle, which means 2 comma 4 is giving slightly higher value.
Yeah, but you also have to do the budget constraint. Now, have you used, you have only used x comma y value and you have put it into the utility function. So it's possible that you may get a higher utility for 2 comma 4, but it is not, maybe it is not supported by the budget equation. So if you have x is 2 and y is 4, so it's 2 plus p is 2, so 8. 8 plus 2 is 10. Yeah, but it is actually satisfying that.
Yes,
2
madam.
plus, yeah, I is 10. Okay, let me calculate this. Give me a moment. I will have to do the computation. So, are you using the calculator on your phone, or are you using the mathematical calculator?
I'm using a calculator on online.
Okay. Let me, I'm also not sure if this is log base 10 or log n. It might be log base 10 also. So, have you used log base 10 or have you used um,
Log base
log?
10 now.
Sorry?
Log base 10.
Log base 10. Okay. This is what, let me open the question. This is 3 log 2. Okay. I don't have my calculator here, but let me try with this. Point 903 plus this is 2y8. Okay, so if I take 2 comma 4, I get 8.903. Okay, and Yeah, so I'm getting 8.43 for the other combination. So yeah, you're correct. We are getting a higher utility. Let's try this. Did you try this with the logarithmic to the natural base?
No, I did not try, but I'm sure it would work similar.
It's not, it's a very small difference. It's not necessary that it would. Okay, x. And let me do this also then. So this is 8.69. Yeah, so if you take natural logarithm, you will get it the utility as higher for the combination given. And they should have written ln instead of log, but that's how it's coming out. So that answers your question.
And
Because
how,
when you're taking the utility maximization, when you're taking the differentiation of log x as 1 upon x, that only holds for natural logarithm. If you differentiate log base 10, you will have to account for that difference also. That differentiation of ln x to equal to 1 by x is true only for natural logarithm. It's not true for log of any other base. So you will have to multiply another factor if you're taking this as log 10. So that's how the calculation is going to change, basically. You understand what I'm saying?
yes, madam.
Yeah. So basically that's the mistake I think which you are making, or it's not clear in the question also. Actually, they have not mentioned ln. But normally, unless they mention the base of the log, you should take it as natural logarithm, because it's rare that you will be given a question with log base 10. Even if they've written log, unless they have written log base something, it's always taken as natural logarithm.
Okay, madam.
Any other question?
And if we get to the seventh question, which is a continuation of that comprehension, o-
Okay.
over there, it was given that the answer is 1 comma 0,
Yeah.
but when I was calculating, I mean, by taking the log for the other values, log, I'm getting non-zero values.
So resolve it with taking logarithm to base natural base first, because you would have taken the same thing in the second part also, right? Log base 10.
Yes, madam. Yes,
Solve it
madam.
using natural logarithm. I think you should get the right answer. I mean, I can solve it, but it will just take time. If you want, if you are not able to get the answer, then we will discuss it. But try solving it first, taking natural logarithm instead of log base 10. It's possible you made the same mistake in this second part also.
Right, madam. Right.
Yeah, because calculation is changing, with natural and log base 10.
Yes, yes. You're true, madam.
Yeah. Okay. Any other questions? Anything else? No. All right. So let's start with today's questions. So let's see if I want to. All right. First, let's do this. So this is an example of. I mean, this question has examples of different plots of cost functions. When I say cost function, I mean cost as a function of Q, quantity. Q is output, quantity produced. And you're asked to determine from the graph which of these, is showing increasing and decreasing returns to scale. The question is, which of the following diagrams is an example of increasing returns to scale followed by decreasing returns to scale? So you can see the four diagrams. There's A, B, and then these are two more, C and D. Screen is stuck. Yeah, so this is C and D. So if you want, you can draw it in your notebook or something, or I can upload it in the folder also. Basically, I want you to just look at the diagrams. Yes, I can't show both. Yeah, it's not zooming out. So if you see, it's like this. Okay, but I can't zoom it to this level. It's not allowing me to. So okay, if you want to look at the diagrams, I'm just uploading this to the shared folder, and you can get the slides from there. And we can refer to the diagrams from there. Okay, I've uploaded it in the shared folder. I hope you have the link for it. Let me just share the link again. Okay, I've shared the link for the shared folder in the chat box. And in that, you can look at week 10. I have uploaded the slides in the folder for week 10. If there is any change, I will upload revised slides later, but this is the slides for now. And because I can't show both the slides at one time, that's why I've uploaded the slides. So coming back, like just look at this diagram and first think about and tell me how will we determine, how will we define whether a given plot of a cost function is increasing or decreasing or constant returns to scale. How do we decide that? And you could perhaps come up with some mathematical way of determining that, but what I'm talking about right now is just basic mathematical and economic intuition. From just basic economic intuition about what is increasing returns to scale, what is constant returns to scale, what is decreasing returns to scale, how do we decide what the cost function might look like? Okay, so just take a few minutes, look at the diagram, and then tell me what you think. Let me know when you finish thinking or reasoning. I'm just giving you a few minutes to think. Done? Any ideas? No? Okay, so let's take a few minutes to think this through. Okay, what do we mean by returns to scale? Earlier, when we defined returns to scale, we referred to it mostly in terms of production function or production technology, right? Let's put it that way. Now, when we're talking about returns to scale, we are still talking about output, right? But we're talking about another aspect of production, which is costs, right? And costs define your, how do I say this? Cost structure or your cost function basically decides how much of inputs are needed to achieve a certain level of output, right? When you're producing something, even when we were using a production function, we were, of course, talking about the inputs, right? How much you vary the inputs and how much the output is varying. That is what we were talking about so far, right? So far, so good. I haven't said anything very new right now. Okay. Now, when we're talking about costs, we are just looking at it a little bit deeper because you see, one of the main factors in production is costs, right? If you're able to achieve increasing returns to scale, you're able to do that because as you're increasing the quantity, somehow your costs are decreasing. And we're not going to discuss too much about how can that happen in the real world, because I know it's very unrealistic in the real world, but it can happen. In some scenarios it can happen, but it's generally rare. Okay, but in theory, increasing returns to scale means that when you increase production or when you're increasing the quantity produced, your cost is actually decreasing. Like, which means, let me just draw this. This is going to require a lot of drawing actually. So as usual, we take cost on the x-axis and sorry, as usual, we take quantity on the x-axis and costs on the y-axis. Now, if I draw a 45-degree line here like this, then that means that if I increase quantity, say suppose this is Q1 and this is say double of Q1, this is Q2 is equal to 2Q1, then costs have also doubled. Okay, so this is C1, this is C2, and this is 2C1. That's what 45-degree line means, right? So far, so good, right? This is not something very mathematically complex. What we discussed, this is there in the lectures. I'm just recapping it now. That when we talk about constant returns to scale, what we mean is that if you write cost in terms of the parameters R, W, and quantity. Let's say I'm writing this in terms of R, W, and quantity, where R and W are exogenous. Then if I take the cost of producing first unit, is given by C, R, W1, right? Now if I increase the quantity to 2, then the cost for the second unit is given by CRW2. Similarly, for producing Q, cost is CRWQ, right? Now, what we know in constant returns to scale is that if you increase the inputs, quantity is going to double. So what you get is that the cost in cost terms, you can say that the cost of producing each unit is the same, right? So you can also say that cost of producing Q units is Q times cost of producing 1 unit. That's perfectly feasible, right? This is what is explained in the lectures also. So it's just a summation of the cost of every unit, and that every unit is same. Say suppose you're making paper clips, okay, very simple example. And the cost of producing one paper clip is say 2 rupees. Then no matter whether you make one paper clip or you make 1,000 paper clips, the cost of making each paper clip is remaining 2 rupees. That's what we're trying to say. So the cost of making 1,000 paper clips is nothing but 1,000 into cost of making one paper clip, which is 2. So it becomes 2,000. That's all we are saying. If that is happening in some scenario, then the function or the production is following constant returns to scale. That is just what we have mentioned here in mathematical terms, which is what I'm showing in the diagram also. If you look at this 45-degree line, this line is basically representing constant returns to scale. Because what is happening in this line? Look at this. If I'm taking quantity as Q1, the cost is C1. And if I'm taking quantity as 2Q1, cost is 2C1. So cost is neither increasing nor decreasing. It is just simply double of initial quantity. Like if it is Q1, it is becoming 2Q1. If it is C1, it is becoming 2C1. So C1 is the cost for producing Q1. C2 is the cost of producing 2Q1. So it is 2 times C1. Okay. Which means that this curve is following constant returns to scale. Is this clear? Any questions?
Is it cost of producing 2 units or cost of producing second unit?
Both are the same. That's what I'm trying to tell you. So in some scenarios, it may happen that, cost of producing the first unit is say 1 rupee and the cost of producing 500th unit is say 3 rupees. Then you cannot say the same thing. But in the example of constant returns to scale, whether you're producing the first unit or whether you're producing the 1,000th unit, cost per unit is remaining the same. You understand? That is why we can say that the cost of 1,000 units is equal to 1,000 times the cost of 1 unit. Did that answer your question?
Madam, I meant what you wrote on the screen, cost of producing second unit, C of R, comma W, comma 2.
Oh, this is 2 units, sorry. Yeah, this is 2 units. 1 minute.
Right. That's it.
Yeah. Yeah, this is cost of producing 2 units. Okay, so now let's see what happens in increasing and decreasing returns to scale as a comparison. So if you understand constant returns to scale, increasing and decreasing returns to scale is not very difficult. Okay, let's draw the 45-degree line again. And let's draw another curve. Say suppose this is the curve. Now in this curve, this is Q1 and this is Q2, okay, equal to 2Q1. Now as per this curve, the pink curve, I'm not talking about the blue curve here now. As per this is C1 and this is C2. Let me write this a little more neatly. If you just look from the diagram, you can see very easily that C2 is definitely not twice of C1, right? Even geometrically, you can just see that C2 is nowhere close to twice of C1. Like this is C1 and this is C2, right? C2 is like very, maybe like 1.2 to 1.5 times C1, definitely not twice of C1. So what happens when you're producing more, you're producing the 2 units instead of 1 unit, cost is not twice of C1, cost is decreasing. This means that you are actually exhibiting increasing returns to scale. It seems a little counterintuitive in the beginning, but it is not if you think about it. Constant returns to scale means if you double input, you're doubling output. Increasing returns to scale means you're doubling input, but you're getting more than double of output, right? That is in terms of quantity produced when we're talking about weight. But in terms of cost, when we're talking about cost, it means that for producing the same quantity, your costs are reducing. First unit, you have certain cost X. Second unit, your cost is not, second unit, when you produce 2 units, the additional unit, the cost is not 2x. The cost is maybe 1.5x for producing 2 units. And then maybe so on and so forth. For the 1000th unit, your cost may be just 1.1 times or whatever amount. Like if your cost for 1 unit is X instead of 1000x for producing 1000 units, it may be just 700x. You have actually reduced your costs compared with the first unit. You understand? Cost per unit is decreasing as you produce more and more units. You can think of it in that way, right? So for first unit cost is say X, then for 1000 units, the cost is not 1000 into X. The cost is something else, less than 1000 into X. That means that if you actually want to produce the same quantity, you are reducing your cost compared with constant returns to scale. Did you get what I'm saying? We're only looking at the quantity produced and costs right now. Okay, so this is the same Q1 and Q2 which we were taking in CRS. So the quantity produced is the same Q1 and Q2, but in increasing returns to scale, the cost is lesser than constant returns to scale, and that is the key takeaway here. So initially we wrote this, right? Let me bring this up. Yeah, C of RW and Q is equal to Q times RC W, C of RW and 1. Now for IRS, this is going to be C of RW Q is less than Q times C of RW and 1. Right, let me write down that example also. If cost of producing 1 unit is X, then cost of producing 1000 units is not 1000x. It's something lesser. Like you can say 700x, etc. This is the intuition basically. The more you are producing, the lesser per unit cost you are getting. You understand? That's the basic idea, basic intuition behind increasing returns to scale. Now let's come to decreasing returns to scale. We'll make the same diagram. Okay, this is not like a line. And let's make another curve. Now in this curve, let's again do the same thing we did. We take Q1. It's also not straight actually. Okay, I hope that sound is not bothering you too much. I can't really help. Okay. Now if you see, in this example, what do you think is happening? This diagram. Q2, let me also write here, is equal to 2Q1. So what is happening as you're increasing production, costs are increasing actually. C2 is more than 2C1, and that is decreasing returns to scale. In this diagram, if you look at C2 and if you look at C1, C2 is more than 2 of C1, 2 times C1. 2 C1 would be somewhere here. This is 2 C1. C2 is clearly more than 2 C1. So, which means that as you're producing more and more, the costs of production are increasing even more, right? As in, like if I take the previous example, if cost of producing one unit or the first unit is X, then the cost of producing 1,000 units is more than 1,000x, meaning it is maybe 1,500x, 2,000x, we don't know, right? That is what we also call as diseconomies of scale, actually. So let me write the equivalent expression here of what we took before. C of RWQ is greater than Q times C of RWQ. So if cost of producing one unit is X, then cost of producing 1,000 units is more than 1,000x. It could be anything, like it could be 1,500x, 2,000x, something like that. Okay, so this is what the concept is. Now, once again, let me open the diagrams. So let me just share the screen itself. I'll annotate on the screen. So, yeah, and this, in this diagram, now you see this part, this is showing constant returns to scale, right? This is just a 45-degree line. The dotted line is the 45-degree line. So this is constant returns to scale. And then it is going up above the 45-degree line. So your basic, you can say like the magic rule or whatever, is that just draw the 45-degree line. 45-degree line is constant returns to scale. If it is steeper, it is above or steeper than the 45-degree line, it is decreasing. And if it is flatter or below the 45-degree line, it is increasing returns to scale. So this part is decreasing returns to scale, right? Let's look at this one. In this part is increasing returns to scale because it is flatter, right? This is increasing returns to scale. Then this part is steeper. It's much steeper than the constant returns to scale. So this is decreasing returns to scale. Then it again becomes flatter. This is again increasing, and then it's almost flattens out to practically constant, or it's still increasing. Okay, so these are all like interesting diagrams. You can see in this till here. This is again very flat. It's below the 45-degree line. So this is increasing returns to scale, and then from here it suddenly becomes very steep. This is decreasing returns to scale. In this till here, you can say it is decreasing returns to scale. Then it is sort of flattening or whatever. It's kind of achieving constant returns to scale, and then it is basically decreasing. The cost itself is decreasing, means this is increasing returns to scale. Okay. So this is like just application of whatever we were discussing till now. You can be given any kind of curve like this. You just have to break it into parts which are increasing and decreasing. So in this diagram, you can see which parts are more than 45 degree and less than 45 degree, pretty much. Okay, any questions about this? Can we go forward then? This is clear? Okay, let's move to the next question. Screen is not updating. Right, okay. So you are given a paper mill which has a production function given by Q is equal to K into L. The cost of renting machinery is R, that is 1000, which means like that is per unit, okay. Wages of workers are W equal to 15, and all values are in the same units, okay. Now you're asked what is the cost, what are the cost minimizing values of K and L if the mill wants to produce 500 units in the long run. So you're given the quantity, you are asked to do cost minimization and asked what are the values of K and L for which cost is minimized. So there's a lot of noise here also. I'm just muting myself for a bit, and please solve the question, then I'll solve it.
Madam, in first question, there is one diagram. I think it's the last one
Sorry, which question?
that you discussed just now.
Yeah.
If you can go back to that slide.
Which one? Okay, the slides are not repeating. Yeah, which one are you talking about?
Option D.
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 Yes.
D for Delhi.
Oh, I have shifted it. The slides are not updating that fast. Yeah. Okay, what about D?
Over here, how can we think of the last part to be IRS? Because it's in the opposite direction. You can't exactly tell if it's absolute
No.
value.
Okay, what is happening in that part? Costs increase up till a certain point, and then what is happening? Costs are decreasing, right?
Yes, madam.
Yes. So in this part, instead of increasing, costs are decreasing. So decreasing cost means what? Increasing returns to scale. Costs are not negative, they're just decreasing. They reach the maximum, this is the maxima. And after that, so this happens many times that, you produce up till a certain quantity, your costs keep increasing. And after that point, for whatever reason, maybe you can buy wholesale or you can do something else. You shift to some other technology of production, whatever, like as in not technology production, you shift to maybe some better machines, whatever reason, after a certain inflection point, like a maxima, your costs actually decrease beyond that point. So what is happening here? The costs are decreasing, right? That golden rule or whatever I told you was just to help you understand what we are trying to do. This is 45 degree and this is above, this is low. In this part, costs were still increasing, but they were increasing at a much lesser rate than the quantity. If your quantity is doubling, the cost is still increasing, but it is not doubling. It is maybe 1.1, 1.2. In this case, the cost itself is decreasing, which means it is definitely increasing returns to scale. Okay.
Okay, Mars.
Yeah. Did anyone solve it? You got the answer? Okay, let's do this then. Let me open the question. So you're given the production function is simply k into L, and you're given R is equal to 100, W is equal to 15, and say Q naught is equal to 500. Okay, you can basically just rewrite this as cost problem. Cost is RW plus KL, right? And you want to minimize this over KL. You can reframe it like this. Now we'll do the same thing which we did before also, which is basically MPK by MPL is equal to R upon W. So first let's calculate MPK. It's a very simple function. So you get L, MPL is equal to K. So we just get L upon K is equal to R upon W. So L upon K is equal to 15. No, sorry. R is 100. Yeah. 100 upon 15. Okay. Then what do? Simply plug in the value of L here, 100K by 15. Okay. Now Q is equal to K into L is equal to K into 100K by 15. Now you're given Q naught. This is 500. This is the value we have to achieve. So this, okay, is the noise too much for you? Are you able to hear me, or is the noise deafening?
We are able to hear you.
Okay, all right. So basically you get k square is equal to 15 into 5, and you can calculate k is equal to 5 into 3, whatever that comes out to be. Okay. So this gives you the answer for k, and then L is equal to 100K by 15. This becomes 3, this becomes root 3, 100 upon root 3. You can simplify this and find whatever the answer Yes, let me see. I think I had it before somewhere. So you can put this as L star. Comes out to be approximately 58, and K star comes out to be approximately 8.66. Okay, so this is the answer. Let's go back to the question. And the second part of the question, you're asked about short run. And the mill can use only 5 units of K in the short run. Because in the short run, capital is fixed, right? And the quantity it wants to produce is still 100. So now how many workers will the mill hire? So I'm muting myself. Please solve it. This is very simple. You can solve it easily and tell me the answer. So did you get the answer? So L will be 100, right? In the second part. I hope everybody got that. Okay, now please do the third part also. In the next short run, the mill fixed K bar at 9. Now, how many workers does the mill now hire to produce 500? And after you solve the second and the third part, I want you to also compute the costs in all the three parts, first, second, and third. See this long run cost in the first part, short run cost in the second and the third part, and then tell me what you get. In the meantime, let me see if I can find a less noisy spot.
Could you please share your screen once of where you did the working for the first part of question 2?
Okay, so I need a few minutes because I'm just relocating to a different room. It's too noisy here. I hope you have solved the question. If you have, then just you can start with the next question. I'll just need 5 minutes to walk till the other room. Okay. Okay. So let me just connect to everything again. Did anybody solve it? Did anybody solve the question? Okay. So I hope I'm audible. I hope I'm audible. Can you just type a yes if you can hear me?
Yes, madam.
Okay. Okay. So let's continue. So did anybody solve the three questions? Did you get any answer? The very simple questions. The first part we already solved. The second part, L comes out to be 100. Now we have to do the third part. Let's do the third part. The second part is pretty simple. You are given K bar is equal to 5. Q naught is equal to 500 is equal to K bar into L. Therefore, 500 is equal to 5 into L. L comes out to be 100. This is second question or second part. Let's go to the third part. In the third part, we see K bar is equal to 9. So remember, in short run, firms will always adjust their capital to achieve a better, a better cost structure, right? Now, let's see what happens in the third part. K bar is equal to 9. Q naught is still 500 only. So Q naught is equal to K bar into L. 500 is equal to 9 into L. L is equal to 500 upon 9. It's little more than 50. Let's see how much it is. I look for the answer. I think I solved it. So this is 55.5. Now let's look at the costs. That is what I was a little bit more interested in. Now, if you see the first part, in the first part, or second part actually, the second part, you can say the cost is CSR is equal to R K bar plus WL. Now R is 100 into 5, right? Plus 15 into 100. This comes out to be 2000. Now let's look at long run costs. This was the part where K bar is equal to 5. K bar is equal to 5. Okay. Long run costs is our K star plus W L star. CLR is equal to R is again 100. K star we had computed as 8.66 and W is 15. L star we computed as 57.73. It actually comes out to be roughly you can take as 58. And cost in the long run is 1731.95 or something like that. So this is, you can see obviously long run costs are lesser than the short run costs. So basically the point I wanted to illustrate is that firms will adjust their capital and labor in the long run to achieve lower costs always, right? And in the short run now, let's see what happens in the new short run. Let's say short run 2. We again calculate the cost. This is 100 into 9. RK, K bar is now 9. K bar is 9, right? 100 into 9 plus 15 into 55.5. This comes out to be, I have computed it also somewhere. Okay, I've not computed this somewhere. You can compute this. What does this come out to be? So 900 plus, let me calculate this. Mm. This is what 15 into 830. This is 900 plus 832.5. So you can see this is lesser than 2000. It's still not probably, let me finish the calculation. Yeah, it's almost the same as long run costs, but only a little bit more, right? It's slightly more than your long run costs, but very close to the long run cost. So this question, actually, I made this question. So this question wanted to illustrate one point. You're kind of seeing how firms adjust capital based on their cost structure in the short run. So in the first short run, the firm kept 5 units of capital for whatever constraint. They could only keep 5 units of capital, and to produce 500 units of output, they had a cost of 2000, right? Now in the long run, when firms can vary everything, they keep they find the cost minimizing values of K and L, and they achieve a lower cost of around 1730, 132, something like that. Now in the another short run, the firms now have the freedom to again adjust capital, but they cannot vary the capital. They can just change it to a new fixed amount, and that new fixed amount is now 9, which is very close to what we took in the long run. And now in the new short run, the firms actually achieve lower costs. So basically, this is what I'm trying to illustrate, that firms keep adjusting their capital in the from one short run to the next, but obviously that cost is still generally a little more than the overall long run costs. Okay, I don't know if that point is clear, but that is what the question was illustrating. Okay, now we come to the next question. The question is, a firm is producing canned foods and the production function is given as 4 root K into L. And the capital is rented at rate R and wages are W. So you are supposed to find the factor demand functions of L and K, the output expansion path for the firm, and the cost function of the firm. So I'll give you a few minutes to think over it, to think about how we will solve this first, and then I'll solve it. So what do you think we will do? What do we mean by the conditional factor demand? So conditional factor demand means it's conditional on what? What are we referring to as the conditional thing here? So remember in Higgsian demand function, when we were determining the the demand functions for different goods, in Higgsian demand we kept the utility as fixed. So in a similar manner, when we're talking about conditional factor demand for L and K, we are keeping output as fixed. So Q becomes Q naught or Q bar, or whichever way you want to denote it. So let me write down the question first. This is question number 3, I think, right? Yeah, question number 3. The function, production function, is given as 4 under root K into L, and capital is rented at rate A. R, W, wages are W. conditional factor demand requires output output to be fixed. Therefore, let's take Q equal to Q naught for the sake of simplicity. Now, what we want is demand functions. Now, before I solve it, let me first explain what do we mean by factor demand. It means that, say a firm is using two inputs, K and L. Then what is the demand function for K and L of the firm? And if this firm is, say, identical in every aspect to all other firms in the industry, there is a certain industry and all firms are exactly identical and they all use only two inputs, K and L, and this is their production function for each firm, then what we are computing is basically the demand function for K and L for that particular industry. If there are n firms, you just multiply it by n. This is basically demand for K and for L of that particular producer or firm. Now, how do we compute it? First of all, we put Q is equal to Q naught. So Q naught is equal to 4 under root K and L. Okay. Now, we also know that we can always use the condition of MPK upon MPL is equal to R by W, because this is the condition for cost minimization. Now let's compute MPK. This is 4 root L upon K. MPL is 4 root K upon L. Therefore, MPK upon MPL is 4 under root L by K upon 4 under root K by L. So this just becomes L by K. This 4 cancels. Root L by K divided by root K by L is, if you just multiply root K by root K, root L by root L, this just becomes L by K. L by K is equal to R by W. Therefore, we can write L and K in terms of each other also, right? So we can, from here, what we get is L is equal to R K by W. Now, what exactly is this? This expression of RK by W equal to L. This is your output expansion path, right? This is what the question is asking. Output expansion path is that if you keep the quantity fixed, or if you change the quantity from Q naught to Q1 to Q2 or Q3, whatever, if you keep the quantity fixed, then in what way are L and K changing, right? Given R and W, which are exogenous. So let me draw this. Say suppose this is, take L here and we take K here. And let me draw this with some other color. Let's take pink. So this is, say suppose, your ISO quants, right? This is Q1, Q2, Q3, Q4. Okay, so far all we've done is we've only used MPK by MPL. We've not done anything else. We've just derived this condition just from using that expression. Now, if we draw this line, what we just got, this expression, it is some line like this. This line is L is equal to RK, R by W into K, which is a straight line of some slope depending on the values of R by W. It can be like this or it can be like that. It depends. Okay, it can be anywhere, but it's a straight line. That much we know. Okay, so this is your output expansion path. What does output expansion path literally means? As your output is expanding, how are K and L varying with each other given your exogenous parameters R and W. Okay, this is what means output expansion means what? As you're moving from Q1 to Q2 to Q3 to Q4, in what way are you adjusting labor and capital? Because there needs to be some relation between labor and capital. You cannot just arbitrarily pick any labor and any capital, right? You will maintain a certain relationship between L and K. And that L and K we are getting from the condition of cost minimization. It's not arbitrary. So that cost minimization gives us a certain relationship between L and K, and as we change the output, how we are varying L and K is given by this green line. As you can see, if you jump from Q1 to Q2, L and K will change in this particular way. You change L from, let me draw it here. If you change L from L1 to L2, then K will change from K1 to K2 based on this equation. This gives the relation or the condition between L1 and L2 and K1 and K2. Okay, now this is output expansion part, but we had to find something else also. We were supposed to find, this is 2, this is say 1. We were also supposed to find, factor demand, right? We were supposed to find the factor demand also. Now in factor demand, we can simply use this condition which we already got. You already got L in terms of K, R and W, right? So Q naught is for root K and L, and we know K in terms of L or L in terms of K. So Q naught is equal to 4 under root K into RK by W. We can write it like this. It's the same thing. Therefore, Q naught, K square under root becomes just K, becomes 4K root R by W. Let me write this better. Now, just readjust this and you get Q naught into root W by R upon 4. Right? This is making sense? So this is your conditional factor demand for K. Now, similarly, this can also be written as K is equal to W by R into L. W W by R into L. Now we just do the same thing and we change the variables. Instead of writing L in terms of K, we write K in terms of L. Now this is nothing but L into this expression. We write K as WL by R. It's 4L into W upon R, and we rewrite the expression to write L in terms of Q naught. This is Q naught into Q naught divided by 4 into R by W. So these are your two conditional factor demand functions. Okay, any problem? You understand how we derive this and what it means? This is how we started. First, we fix the quantity. We fix the quantity to Q naught, and next we took the condition of MRTS equal to R by W. This comes from cost minimization. So when you differentiate this, you get L by K is equal to R by W. If there's some other production function, you will get something different, but you will get some sort of a relation between L, K, R and W. So in this case, we get a very simple relation. L is equal to RK by W, or K is equal to WL by R. This gives you the output expansion path, and Using this output expansion path, we substitute for the value of L first to get the conditional factor demand for K, and then we do the other way down. We substitute for K and we get the conditional factor demand for L. Okay. So this conditional factor demands basically tell you what? That if a firm is planning to produce a certain quantity and wages and rents are determined by the markets, then how much would be the demand for that particular input? In this case, it is L and K, it could be some other input, it could be X1, X2, or whatever. Okay. Is this clear?
Yes, madam.
Okay, good. So next question is asking you something very different now. There's a question from the Andrew Scotter book. I think maybe I've not put it in the references. I'll check. If it's not, I'll add it. So this question basically says Solo Industries owns 3 plants at which it produces gliders. Okay, plant 1 has an average cost function given as this. Plant 2 has an average cost function given as this, AC2 equal to whatever, and plant 3 has an average cost function given as whatever. Okay, it's given the functions. Now, Solo receives 3 different contracts to produce gliders. One contract calls for 8 gliders, second for 12 gliders, and the final one calls for 18 gliders. Now, if each contracts glider, there should be an apostrophe there. If each contracts gliders must be produced at one plant, to which plant should each contract be assigned? So I'll give you a few minutes to think about this. What are we going to do here? So what will we do in this example? They're given the cost function of each plant, and you're given the quantity for the 3 contracts. Each contract has a different quantity of gliders to be produced. So what is the firm going to do? What is ideally what that the function that the that the firm will want? For each glider contract, like the 3 contracts are 8, 12, and 18. For each contract, the firm will want to minimize the cost, right? And each firm has 3 ways of producing the same contract, right? Let's do this as a table. I open the question again. should. Okay, so let's write this. Average cost for the first plant is minus 24q plus q square. Average cost 2 is 200 minus 32q. It's 2q square. Average cost 3 is 200 minus 40q plus 3q square. Right, these are the three cost functions. Remember, this is average cost, okay, not total cost. Total cost will be average cost into q, right? Now you are given quantities q1 equal to 8, q2 equal to 12, q3 equal to 18. So what are we going to do? It's a lot of calculations, but it's interesting question. What will we do? We will calculate the costs for each quantity and each plant. So for plant 1, you will calculate the cost for Q1, Q2 and Q3. Then for plant 2, you will calculate the cost for Q1, Q2 and Q3. Then for plant 3, you will calculate the cost of Q1, Q2 and Q3. Let's make this table. And hear me? I think my Wi-Fi broke in the middle, so just give me a minute. My iPad is disconnected. Can you hear me?
Yes, madam.
Okay, let me just connect the iPad again. Okay, this is connected. Okay, so you understood what I was doing, right? We just compute the costs again for each plant and each contract. This is the table I was making. Let's make this a little bit neater. Okay. It's not very neat, but I think we can work with it. Okay, so much for housekeeping. Now, this is the part where you have to do a lot of mathematical calculations. You can write the total cost function for each of these. Let me write that also. Or let me move this down a little. First write that. Write the total cost function. TC1 is 200 q minus 24 q squared plus q cube. Total cost 2 is also 200 q minus 32 q squared plus 2q. Okay, these are your total cost functions, and these are the quantities. So you will have to do a lot of maths. For each value of q, you compute these costs. So I am also doing this, but I want you also to please calculate this. This is like a little cumbersome, but it will be helpful if you do this. You will kind of know where we are headed. Okay, I'm doing the calculations also. I'm muting myself, and I want you to also do it to cross check the answers. Actually, we don't need the total cost. That's what I just realized, because you're multiplying each one by the same quantity. So you can do just the average cost also. This is strictly not needed. You can just calculate the total cost instead of, sorry, the average cost instead of the total cost, because we are just comparing it. So this will not be 576. Oops. Okay.
We may actually be needing total cost because all the average cost values, if they are equal, how can we differentiate between
Sorry, what?
we may actually need a total cost because
No, we will not need the total cost because for each quantity you're comparing the cost between the three plants. First compute it, then I will explain why you don't need the total cost. Okay, so you see the pattern, right? I'm just filling in the last part also. It takes a little bit time to calculate. So I'm just um, filling in the values. You can check if you're getting the same answer. So coming back to what the firm will do, you're comparing between the cost among the cost of plants 1, 2 and 3 for the same quantity. So if you multiply each of these cost values by Q1, you're still comparing the same thing, right? 72 Q1, 72 Q1, 72 Q1, it doesn't make a difference, right? That is why I said you don't need the total cost. You can actually use just the average cost. Now for Q1, that is the first contract, the plant has the same, all the plants have the same costs, right? They're all 72. So for the first contract, the firm is going to be indifferent between choosing plant 1, 2 and 3. Okay, so we will come back to the first contract later. Let's look at the second contract for Q2. This is equal to 12. For Q2 equal to 12, you can see that definitely plant 1 has the lowest cost, right? So the firm will want to choose plant 1 for fulfilling the second contract. For the third contract, also, I think this is, 1 minute, let me check if this is the correct answer. Yeah, this is the correct answer. For the third contract, you can see that Again, plant 1 has the lowest costs. This is the one which has the lowest costs, right? So what is the firm going to do? Hmm? Oh, no, sorry, this is, no, it's correct, sorry. I thought I have made a mistake. Right, so what is the firm going to do?
It's going to produce both the second and third contract gliders in plant 1.
Not really. Okay, there is, I think, a mistake in this question because what answer they have given is wrong. They're saying that, yeah, I mean, it is contract 2 is best fulfilled in plant 2, but that is not so because, yeah, there is a mistake in the question. Well, there is a mistake in the question, and I'm very surprised that a book will have a mistake in the question because these answers are correct. I'm getting the exact same values as what they are getting, but they're mistakenly written that for contract 2, the cheapest way to produce is using plant 2, which is not the case, right? So, anyway, if let's assume if that were true, if these values were swapped, then firm would produce second contract from plant 2, third contract from plant 1, and the first contract from plant 3. Okay, but that is not the case, and this is really not my mistake. This is just wrong in the book. It's a solved example in the book, and I'm surprised they have made this mistake. But either way, if in this case, if we take the numbers as it is, for the third contract, the firm can definitely use the first plant. For the second contract, the firm would also prefer to use plant 1, but since they cannot use plant 1, they will choose plant 2, which is the second option after plant 1. And for the first contract, they are indifferent between all of them. So now only plant 3 is left, so they will use plant 3. You got what I meant? So they will use this one for plant 2 because they can produce one contract from any one plant. They cannot produce two contracts from the same plant. So this is how they can achieve the lowest costs, right? If you add 56 plus 272, you get a higher number than if you add 104 and 92. That's probably the logic you can use. Okay, enough with this question. Let's go to this is, I think, there are two related questions, still like the last few questions. So you're given a function q is equal to f of x1, x2. You're asked which of the following statements is or are true about the firm's cost. So I'll just let you read it and think a bit for a few minutes. Okay, my iPad is not connecting for some reason, so I'm just going to share the screen here itself. Just give me a moment. So I hope you can see my screen. There's not much to write in this anyway, so I'm not connecting my iPad now. There's some issue with the iPad internet. So can you see the screen? So if you see, let's go to the question. The first part is the long run cost is always going to be equal to or lower than short run costs of the firm. This is true, right? Because that is the whole point of long run cost. If you look at this diagram, this is a diagram in which we are plotting average cost against quantity, and the dark green curve is the long run average cost, and the other curves are all short run average cost, SRAC 1, 2, and 3. And the pink curve is a short run marginal cost for first run. And if you see this diagram, this answer will be pretty clear that long run average costs are always going to be lower than the short run average costs. Then second option is there is a unique value of output for which short run and long run costs will be the same. And that is true because you see short run average cost curves are tangent to the long run average costs at some point, at any one point basically. That means tangent means they're not intersecting. The tangent means there is only one point at which they're going to be touching the long run average cost. And the third option is depending on the form of the production function, there may be no level of output for which long run costs are the same as short run costs. Depending on the form of the function, there may be no level of output for which long run costs are the same as short run costs. Now, I think this is true. I'm not exactly sure, but I think this is true. We leave C for the moment. For the fourth part is the output level at which long run and short run costs are equal. The firm is minimizing its cost of production. Now, this is not always true because if you again look at this diagram, the short run average cost curve can be tangent to the long run average cost curve at any point, not necessarily at its minimal point. It may be the minima of the short run average cost curve or it may not be. So there is no guarantee that it is always going to be the minima at which it is tangent to the long run average cost curve. Okay, this is the last question. It is based on the same kind of logic. You're asked if these statements are true. The long run average cost curve is the envelope of the short run curves, which is true. That is the whole way we have defined it, and you can see it is enveloping all the curves from below. Output Q2, at output level Q2, the firm will choose to produce using capital corresponding to SRAC3. Now let's see what is happening in Q2 level. At the level Q2, you can see that the short run average cost is much lower than the short run average cost in the third run, SRAC3. You compare SRAC3 with SRAC2, that dotted line from Q2, it's intersecting the blue curve much lower than the brown curve, which means that the cost associated with the second run is lower. So it is not going to produce at capital corresponding to SRAC3. So B is not true. Producing at the level Q2 is more cost effective for the firm than producing at Q1 when it is using capital corresponding to SRAC2. Let's see SRAC2. SRAC2 Q1 costs are much higher than Q2, right? Let's go back to the question. So Q2 is not more cost effective than Q1, right? Q1, no, sorry, the other way around. Q2 is more cost effective than Q1 because the cost associated with Q2 in the second run is much lower than the cost associated with Q1 in the second run. Let's just look at where the dotted lines are intersecting the blue curve. Okay, all SRAC curves touch the LRAC curve at the lowest point, which is not true. We just discussed that. The
Madam, can you
SRAC,
give a counter example for this? Why it is not always true?
I can't give you an example because for that I'll need to create a whole like cost function, and I can't just make up any cost function. I will need to think about that. But I mean, if you think about it, that then the long run average cost is basically minimizing at the for a longer time interval, right? So it is going to achieve lower costs on the whole for the entire path. But at one particular point in the short run, you may be able to achieve lower costs, using some other combination of inputs. Okay. And the last point is the short run marginal cost curve intersects the short run average cost curves at their minima. This is true. This is because if you just do the maths of it itself, you can work it out. It will intersect it at that exact same point. Okay, so this is like all the questions I had for today, and I think we are kind of done. So I hope this makes sense. For the question you asked, like try to take some example from a book or something and see how it is coming out to be. It's not that it is never true. It is that sometimes it may not be true. It may or may not be tangent at the minima. That's what the question is saying. It's not mandatory that it will be tangent at the minima.
The examples that we have been shown in class till now, they always had it touching at the lowest point, which is why I asked you this.
Yes, so that's what I'm saying. That may be commonly true, but it is not always true. That's all. That's what I'm saying. It depends on the function. The functions you have taken till now are very simple functions, right? It may not always be the case that it is tangent at the lowest point.
Okay, madam.
Yeah. Okay. All right. So if there is no other question, we will meet again next week. And in between, if I get a resolution on the assignment 8 question, I will post it in the notes. All right. Thank you.